Greetings everyone. This project is focused on identifying hate speech in low-resource languages like Sinhala, and this is a course project for course Algorithms and Artificial Intelligence DS 303. Sentiment analysis has seen widespread application in high-resource languages. Its significance becomes even more important in the context of low-resource languages. And amongst these languages, Sinhala, spoken predominantly in Sri Lanka, emerges as a particularly noteworthy case. Low-resource languages, often lacking extensive linguistic resources and label datasets, present unique challenges for sentiment analysis. The scarcity of available tools and datasets make it even difficult to develop accurate and contextually relevant sentiment analysis models. Despite these challenges, the importance of sentiment analysis in low-resource languages cannot be overstated. Moving on, this project is aimed to answer two key research questions. Question 1. How can we effectively forecast sentiment in Sinhala text using machine learning and deep learning techniques? Question 2 is what impact does the alteration of established deep learning models through the stacking of similar and dissimilar models have on overall performance? The basic overflow of this project is as follows: data collection, data preprocessing, exploration of ML models, exploration of DL models, and evaluation of these models' performances. Let's have an overview of the dataset. The Sinhala Offensive Language Dataset (SOLD) is a manually annotated corpus of 10,000 Twitter posts in Sinhala. Each post is labeled as offensive or not offensive at both the sentence level and the individual token level. Data characteristics. The data set contains the following columns: post ID, which is the unique Twitter ID of the post; text, which is the full text of the post in Sinhala; tokens, the text divided into individual tokens separated by spaces; rationals is a binary indicator of each token where 1 indicates offensive token and 0 indicates a non-offensive token. Label is a sentence level label, either if the text is offensive or not offensive. In this project, the columns of focus were text and label. The data source is Hugging Face. This section outlines the specific preprocessing techniques employed in the study to enhance the quality of Sinhala language dataset. First, removing non-Sinhalese characters. Filtering out characters that do not belong to the Sinhala script eliminates noise and ensures data coherence. It also enhances the effectiveness of subsequent analysis. Second is removing the stop words. Eliminating the common words with minimal semantic value reduces the data dimensionality and focuses on content-bearing words. And the third is tokenization, basically breaking down the text into individual units. Moving on to the exploration of ML models, firstly, TF-IDF, Term Frequency Inverse Document Frequency, is a widely used statistical method in natural language processing. It measures how important a term is within a document relative to the collection of documents, that is, relative to a corpus. TF-IDF features of data were used to train these ML models. Let's look into the ML models. Logistic regression, a linear classification method ideal for both binary and multi-class problems. XGBoost, a scalable ensemble learning approach. XGBoost efficiently uses gradient boosting with decision trees for robust predictive modeling. Decision tree divides the feature space based on significant attributes, offering an interpretable structure for classification and regression tasks. Random forest is a versatile ensemble technique. It combines decision trees to enhance predictive accuracy and minimizing overfitting. Support vector machine (SVM) classifies data by finding the optimal hyperplane, making it effective for linear and non-linear classification tasks with kernel usage. Then we have Gaussian knife Bayes, a probabilistic classifier based on Bayes' theorem, suitable for text classification and spam filtering assuming feature independence. AdaBoost strengthens weak learners into a robust classifier by iteratively adjusting weights on misclassified instances, improving adaptability. Gradient boosting. Similar to AdaBoost, gradient boosting sequentially builds decision tree ensembles, optimizing for residuals to create a powerful predictive model. K-nearest neighbors (KNN) classifies data points based on their majority class amongst the K-nearest neighbor, a straightforward and effective algorithm for classification tasks. This table displays training accuracy, validation accuracy, test accuracy, and F1 score for the models mentioned before. Though the training accuracy reached even 0.996 in models like decision tree and random forest, their validation accuracy or test accuracies could not maintain the same margin. It can be seen that this suggests a model overfitting. Logistic regression has achieved highest test accuracy among all the ML models with 0.684 and a decent F1 score of 0.574. Moving on to the deep learning models. Following models will be discussed in the further video. Firstly, ANN. Artificial neural networks along with TF-IDF embeddings contribute to this model's ability to predict hate speech. Specifications of the model are as follows. There is one hidden layer with 100 neurons, and the activation function used is ReLU, Rectified Linear Unit. As can be seen on the screen, this model gave about 0.634 accuracy and an F1 score of about 0.579. It could be considered as a base margin for the further deep learning models. Here, two models are displayed, both sharing the same architecture layer-wise but differing in hyperparameters and features. In the first model, the output dimension parameter representing the size of the embedding vector for each word is set to 128. Meanwhile, in the second model, it is set to 300. The embeddings used in the second model are generated through word-to-vec, a technique applied to convert words into dense vectors based on their contextual usage. Later on, an LSTM layer is followed by a dense layer. The performance of these models is as follows. The first model, which is just LSTM, gave an accuracy of about 0.734 and F1 score of about 0.693. The LSTM model, which also included the word-to-vec embedding, gave an accuracy of about 0.577 and F1 score of 0.409. Let's now look at LSTM plus CNN models. Here, a consistent architecture is maintained across both models layer-wise, but again differing in hyperparameters and features just like in the previous set of models. The flow is as follows. Embedding layer, convolutional layer, max pooling layer, LSTM layer, and two dense layers. Here, the second model used word-to-vec embedding. The performance of these models is as follows. The LSTM CNN model, which doesn't have word-to-vec embedding, gave an accuracy of 0.729 and F1 score of 0.657, whereas LSTM CNN with word-to-vec embedding gave an accuracy of 0.576 and F1 score of 0.178. These numbers help us conclude that word-to-vec embeddings are of no asset to the models. Carrying forward the LSTM CNN model from before, there is a minor layer change here. We have the embedding layer, the convolutional layer, the max pooling layer, the LSTM layer, but now instead of two dense layers, it is cut down to one dense layer, and the differences in hyperparameters is as usual. The LSTM CNN1 model showed great results and an increase in F1 score from 0.657 to 0.685 from the previous model. Here, there are two LSTM stacked architectures. The first has the layer stack as follows. Embedding layer, LSTM layer 1, LSTM layer 2, and the dense layer. And then the second architecture has the layer stack as embedding layer, LSTM layer 1, dense layer 1, LSTM Layer 2 and Dense Layer 2. There was an increase in not only F1 score but also in accuracy this time. LSTM Stack 1 accuracy was about 0.744 and F1 score was about 0.719. It was also observed that having the dense layer in between the LSTM layers has led the F1 score to drop down to 0. Then comes the thought of changing the course of experiment and to try something different that could help get better results. And that's when the pre-trained BERT model came into picture. These two models have the same architecture but different hyperparameters, and can also be seen there is a major increase in accuracy and F1 score compared to the previous models. As now the accuracy is 0.794 and F1 score is 0.781. Building on the previous model, additional 2 extra layers were added to the architecture, a CNN layer followed by an LSTM layer above the BERT. And finally, this architecture has given by far highest accuracy of about 0.800. Now, as we come to the end of the video, it's time that we answer the research questions addressed in the beginning. First, how can we effectively forecast sentiment in Sinhala text using machine learning and deep learning techniques? As seen in numerous models of machine learning and deep learning throughout this video, it can be said that sentiment analysis in Sinhala text excels with an accuracy surpassing 80% when combined with LSTM, CNN, and BERT architectures. This approach can be said to be highly effective and robust. Second, what impact does the alteration of established deep learning models through the stacking of similar and dissimilar models have on overall performance? The architecture of a composite deep learning model significantly influences its accuracy. It was observed that there were instances where the F1 score of certain models declined to 0. However, through meticulous adjustments of hyperparameters and modifications to the model structure, it was possible to achieve substantially higher accuracy than what each individual model could attain. This highlights the importance of thoughtful model design and parameter tuning in maximizing the overall effectiveness of combined deep learning models for tasks such as sentiment analysis. This wraps up the study about identifying hate speech in low-resource languages like Sinhala. This study was conducted under the guidance of Dr. Animesh Chaturvedi. I am Induri Janvi from the Data Science and AI batch of 2021. Thank you.